Welcome to classes on physics, HS second year, and it is the continuation of class number 1, and the topic is dual nature of radiation and matter. So today I will chiefly concentrate on the mathematical part of this chapter, and the mathematical part is very interesting, and lots of questions are being asked in the class as well as in entrance exam point of view. So before going to the original part, let me once again summarize some of the key points. Now let us see some of the key important formulae of the dual nature of radiations and matter. H nu is equal to Ke equal to work function, and sometimes it is phi naught. It is all the same. And again, H nu is equal to kinetic energy plus H nu naught, because nu naught is equal to work function equal to H nu naught equal to threshold frequency. Again, kinetic energy is equal to H nu naught, H nu minus H naught. Again, kinetic energy is V naught. Again, E V naught is equal to H nu minus H nu naught. Again, H nu equal to 140 electron volt or nanometer, and sometimes it is written 1,242 electron volt. It is calculated. You need not to calculate Planck constant 6.62 into 10 to the minus 34 joule, and velocity of light equal to 320 Fahrenheit. It is well calculated in this way. Again, this part is from photoelectric effect, and this part is from lambda is equal to h by mb, de Broglie hypothesis. De Broglie's wave equation equal to h by p equal to h by root over me. In the last class, I have deduced the relation equal to h by twice m e v naught. Again, h equal to twice m e q v. So a bit difference here I am telling that when the wavelength is related to energy, kinetic energy, you apply this formula. When wavelength is related with the potential applied, and you apply this formula, and this is chiefly based on the electron when it is moved in the across the potential applied in the system, and this is in place of E, it is Q when it is proton and alpha particle except electron. If it is besides electron, something other having charge is asked in the question, then you apply this one. Very often you is confused which one is applied in which time. It is for electron, it is for the other than electron, proton, deuterium, protium, proton or deuteron, or sometimes alpha particle and proton. At that time you apply this formula, otherwise this formula. Am I right? Again, in short, lambda is equal to 1 by lambda is equal to h by twice m e v q b. Am I right? So lambda is proportional to 1 by root over b, 1 by root over b, and if you put the value of this one in terms of Armstrong, you will find 12.7 by root over b into Armstrong. It is very important, and it lessens a load of calculating a lots of things, so please try to keep it in your mind. Again, fractional part of this is equal to W naught equal to H nu naught is equal to C by lambda naught. Nu naught is equal to threshold frequency, and lambda naught equal to threshold wavelength. Mind that threshold work function for each metal is fixed, it doesn't vary. Am I right? So it is constant for one metal, and metal to metal it is constant, and number of the electron emitted is equal to power by energy, and this n is equal to number of the electron ejected, p is equal to power of the radiation is equal to energy of the radiation, or you can write p is equal to h nu. Again, you may write h equal to c by lambda. A lot of things you can write yourself. Again, ejections occurs when the radiation has energy h nu is greater than the threshold frequency or work function of the metal, and if this thing is satisfied, then electron will be ejected, otherwise electron will not eject. Or the radiation of the frequency is greater than threshold frequency of the metal, then the ejection will occur. Or h by c lambda is greater than this, means uh, uh, um, This is lambda of the incident radiation, and this is the lambda of a threshold lambda wavelength. Am I right? Another point, it is very often asked in exam, nature of electromagnetic radiation is established by the phenomenon, and this phenomenon is called photoelectric effect. So this is of about the background of the mathematical formulation of this chapter. Before coming to the main part of the solution, mathematical solution of this chapter, let us tell something about wave theory which cannot explain photoelectric effect. And which are the facts on which the wave theories fail to explain the photoelectric effect, very often asked in the exam. I am telling you in short. So, in order to explain the some loopholes or the wave theory, general classical wave theory, which cannot explain the photoelectric effect only because of the fact that in the according to wave theory, it is consist of sub wavefronts, and these wavefronts are uniformly distributed with energy. When the intensity of high energy of radiation is used, then generally what's happened, the amplitude of the wave increases. Along with the increase of the amplitude of the wavefronts, what's happened, the energy content or stored of energy in the systems also increase. Along with the increase of the energy in the system, the energy of the electron increases. That means kinetic energy of the electron is directly proportional to the intensity of the light. But in actual practice, experimentally, it is found that the energy of the electron is independent of the intensity of the light. So this is why wave cannot explain the photoelectric effect. And second point again is very vital. The energy of radiation which is transferred in the system is transferred of the system does not transfer to a single electron. It transferred to the system of electron as a whole, and energy is uniformly distributed to it all electrons. So during the ejection of electrons, so electrons should be energized fast. So in the way of energization in terms of the wave theory, it requires a bit time. But experimentally, it is found that as soon as the light of suitable wavelength is fall upon the surface of the metal, the electron ejects out, and the time lag between the incident of the light and ejection of electron, it is equal to 10 to the power minus 10 second or 10 to the power minus 9 second. It is very short, and it is an instantaneous process. These are the two things, or especially in a nutshell, are the facts which. So now, well, how this photoelectric effect, that is photon nature, explains the fact successfully. Number one, very simple. The explanation is that in the interaction of the photon with the free electron, the entire energy of the photon is absorbed by the electron. That's why electron instantly jumps from the system or from the metal surface within a fraction of the time, 10 to the minus seconds. Number two, the energy of the electron is proportional to the frequency of the radiation, not to the intensity of the light, because the E is equal to h nu. So it depends upon the frequency of the radiation, not upon the intensity of the radiations. So this is the part which I have in short explained. Now let me come to the mathematical part. Yes, the question is lambda 1, there are three wavelengths, lambda 1, lambda 2 and lambda 3 are given. With threshold wavelength of metal is also given, and you are asked which light will able to eject electron. So first of all, your target is to find out the light required or energy required to eject out electron from the metal. What is metal wavelength? Metal wavelength is 600 nanometer. So E is equal to hc by lambda. So I have calculated the energy required to evolve or eject electron from the metal surface is this much. Now let me check what is the amount of energy corresponding to lambda 1, lambda 2, lambda 3. For lambda 1, with respect of lambda 2, and with respect of lambda 3, let us find out. If you calculate, you will find it is approximate. So electron need to be ejected, the amount of energy need to be is required for ejection of electron from the metal is this much. So this 2 energy is above this energy, but this energy is below the minimum frequency of energy of electron where metals wavelength 690 nanometer. So wavelength lambda 1 and lambda 2 will able to eject out electron from the metal surface, because the energy required from the metal to eject electron is 2071 and that energy is less than this amount. So this is the minimum requirement of energy is to be supplied up to eject electron from the metal surface. Am I right? So these two wavelength will able to eject out electron from the metal surface, and this amount of energy or wavelength having this about 600 nanometer is unable to eject electron from the metal surface. It is very simple, just you strike the point, you can get the answer. It is known to us to all. So I am writing 1 electron equal to 1.6 10 to the minus 19 joule. So question is, threshold frequency of a metal is 450 electron volt. What will be the frequency of the incident radiation to eject electron with minimum or maximum kinetic energy 6.06 into 10 to the power minus 19 joule. Let us write the formula. H nu is equal to, so this is the formula, very simple. Here nu is the frequency of incident radiation, kinetic energy of the kinetic energy is the, it is the kinetic energy is the kinetic energy of the electron, h nu naught, work function of the metal. Now what is given here? H nu is equal to kinetic energy is given. But one thing before starting to doing the problem, first of all you see that threshold frequency is given in terms of electron volt. So beforehand I told you that one hc is equal to hc, the value of hc is equal to that is electron volt nanometer if the wavelength is given in nanometer, and if wavelength is if the frequency of a metal is given, if the threshold frequency of the metal is given in terms of uh, electron volt, it should not be threshold frequency, it is work function, because it is electron volt, it is energy. Work functions of a metal is this much. So if it is electron volt, then you should convert this joule into electron volt and so also a Planck constant into electron volt. These two things you need to do and nothing else. So you show h nu is equal to kinetic energy plus this, then kinetic energy is equal to how much? Kinetic energy equal to this much. So you see kinetic energy is equal to 6.06 into 10 to the power minus 19 joule, that is equal to 6.06 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19 joule, and that is equal to so that amount is equal to 3.8, and that h nu is given to you equal to 4.50 electron volt. So that much is equal to this. Therefore nu is equal to divided by h, where h is equal to 1/4. It is joule per second, so that joule should be again divided by so the value of h here, that value of h here is equal to 8.314 divided by 16 10 to the power approximately. If you calculate, you will find this much hertz. So very simple. The key point is just you try to convert the kinetic energy in terms of electron volt by dividing it by 1.6 into 10 to the minus 19, and Planck constant 8.314 10 to the minus 34 is again should be divided into 1.6 into 10 to the minus 19, approximate value. Here is the question. Before doing the problem, just I am showing you there was the same type of question in the NEET 2023. A question was asked here, but in the question in place of calcium it was given somewhat cesium, and the answer cesium was the correct answer in the NEET 2023. Maximum of the student could not answer the question, but I will tell you the complete way how to solve. Light wave of wavelength this nanometer falls upon the following metals. This same light wavelength has been fallen upon the surface of the metal sodium, potassium, calcium, molybdenum with given work function of this much, means this is the minimum threshold frequency when fall up with some minimum threshold frequency when fall upon the metal, then work function is found to be 192. Below this value electron will not eject, above this value will eject. Below this value electron will not eject from potassium, but above this value electron will eject. Below this value electron will not eject, but above this value electron will eject. So from which metal electron will be ejected out if the light wave of incident light wave of this much nanometer is fall upon this one. So let us first of find out the what is the energy involved with this light one. E naught involved with this light is equal to hc by lambda. Hc is equal to 1240. Very simple. Electron bond nanometer, and since it is given in terms of nanometer, so the wavelength is 512 into 5 nanometer. It is approximately, I think, 3 electron volt. So the light which has been fallen upon the each metal individually has the energy or work function that is 3 electron volt. So now you compare 3 electron volt. This too much is, these two values are more than this. So the light which has fallen upon the metal surface with this much of energy will not able to eject electron from this one, because this value require more value of this incident light energy. So light will be evolved out from sodium and potassium. But in the question, I think it is a wrong data. Data is given wrong, because the work functions of sodium should be greater than this. I think this should be 230. You make it correct, because the logic behind this is the question. It is given in this way, but it should be greater than sodium potassium. Am I right? It should be greater than this one. Greater than this value, but it is given 1.92. No matter, this will also eject out electron. If it is 230, again it is less than this amount, so it will eject electron. This amount of light has higher energy. Incident light energy is higher than that given work function. Am I right? So why sodium should have a higher work function than this one? Because sodium, potassium, rubidium, cesium, francium all are in the same group. When you move from top to bottom in the group, the size of the element increases. As the size increases, the outermost electron go further and further away from the nucleus. So outermost electron, when we will try to eject out, are loosely bounded from the nucleus, so less amount of energy will be required to eject out the electron as size increases. So if that should have less, it has smaller size than this one. So in terms of size, it is bigger. Am I right? So bigger, if size is bigger, then electron is loosely attracted by the nucleus, so less amount of energy should be attracted. So if I give it more energy to sodium, because the size is more tightly attracted by the nucleus, more amount of energy will be required. So that should not be 1.92. I think it should be 2.30, like this. Anyway, if you give it this, answer will be same. The electron will be ejected by sodium and potassium. But fact is that if the elements are in the same groups, and if the size increases, the outermost electron will be much more further and away from the nucleus, and attractive force of the nucleus will be towards the nucleus. Attractive force of the nucleus towards itself will be the smaller or weaker, and less amount of energy will be required to eject out electron from the metal surface. Very simple question, just you try to follow the question. Light wave of the incident frequency is nu. It is given. Work function is W naught, and kinetic energy is K. It is given. And you are asked what will be the kinetic energy of the frequency if the frequency kinetic. What will be the kinetic energy if the frequency of the incident radiation is double from the initial. So you see, H nu equal to kinetic energy plus W naught. As per the question, H nu is equal to kinetic energy should be assumed as K, and nu is nu, and what is work function is equal to W naught. So what you are asked, say it is 1. You are asked what will be the kinetic energy. From here you find out kinetic energy. Am I right? Kinetic energy is equal to H nu minus this. Am I right? What will be the new kinetic energy if the frequency of the light is double from the initial frequency? So I have made it double. Am I right? So this is twice H nu equal to W naught equal to twice. Again, now H nu is equal to this much. You put the value here, K plus W naught minus W naught twice K plus twice W naught minus W naught twice K plus W naught. Means you mind that this type of questions very often asked in the entrance exam. Very simple. The new kinetic energy when incident light, the frequency of the incident light has been doubled from the initial one. It will be the twice of the initial kinetic energy. This new kinetic energy is twice of the initial kinetic energy plus work function. Am I right? This is simple. Nothing to explain more. Again, very simple, and it is a very typical question. It is a simple and short. The photon of energy, 1 electron volt, 2 electron volt, 2 photons. The energy is something different. One is 1 eV, other is 2 eV. Successively incident upon the metal surface of the work function 0.5. What is the ratio of the kinetic energy? Say for kinetic energy, U1 equal to Hc minus W naught. The photon energy 1 electron volt. The photon energy, if it is 1, that is energy 1, am I right? That energy 1 is equal to 1 electron volt, and work function is equal to fixed 0.5 electron volt equal to 0.5 electron volt. And for kinetic energy 2, very simple, H nu naught minus W naught. Now that H nu naught, this is H nu naught energy equal to twice electron volt minus W naught equal to 0.5. Am I right? And this is equal to 1.5. Am I right? So E1 by E2 is equal to 0.5 divided by 1.5. Multiply by 2 and 2 above and below denominator and numerator, so you are getting 1 by 3. So it is 1:3. Nothing to explain again. It is very simple. Just you put the relation and put the value, place the value 1 AB in one place and 2 EB in another place, subtract it and find out K1 and K1 and K2. You will get it very easily. Very simple, nothing to explain. But again, this is the question very often asked in all India level questions, and also in the entrance level questions. Don't get nervous to solve out the problem if you have the concept. The new incident upon the metal A and B, two metal. One metal has the threshold frequency nu by 2, another metal has the threshold frequency. Metal A has a threshold frequency is nu by 2, and metal B threshold frequency has nu by 3. You were asked to find out the energy. So K1 is equal to H nu naught minus W naught. Am I right? So H nu is equal to, what is nu for K1? That is for metal A. So you write is what as kinetic energy for metal A is equal to H nu naught minus H nu W naught. H nu naught, here H is constant, nu is equal to W by 2 according to question, and this is W naught is equal to H nu minus H nu naught. Am I right? For the first case, H nu, and threshold frequency for metal A is nu by 2. Nu by 2, and that is equal to twice H nu minus H nu by 2 is equal to H nu by 2. Now for kinetic energy for metal B is equal to H nu minus again H nu naught, and for the second case this is H nu, here frequency is equal to given lambda by 3 equal to thrice H nu minus H nu divided by 3 is equal to twice H nu divided by 3. Therefore Ka by Kb is equal to nu naught 2 by H nu divided 2 by twice H nu divided by 3. I think this is 3 by 4. Very simple calculation. Again, you can do very easily in exam. Again, very simple. Just I am explaining. Threshold wavelength for the two photosensitive metals A and B are lambda 1, lambda 2. That is for metal A, the wavelength is lambda 1. For metal B, its wavelength is lambda 2. You are asked to find the work function. What is the formula for work function? Work function is equal to W naught equal to H nu naught. Am I right? So W naught A for the metal work function for the metal A is equal to H nu naught, where H equal to nu naught is equal to C by lambda. For that metal, it is told as lambda 1. So I have put here lambda 1. So work function again equal to H nu Hc by lambda, and that lambda is for the metal B is equal to lambda 2. So lambda Hc by lambda 2. If you divide Wa by Wb is equal to lambda 2 by lambda 1, again it is very easy as like as flow of water. The question is again is very simple. First, you try to understand kinetic energy of photoelectron is double for a metal when wavelength shift from lambda 1 and lambda 2. Deduce an expression for the threshold frequency and work function of the metal in terms of lambda 1 and lambda 2. Very simple. The question is that when the wavelength was lambda 1, kinetic energy was K, and when wavelength changes to lambda 2, that kinetic energy become twice K. This is the condition, and you are asked to find out an expression for threshold frequency means lambda naught, and you are asked to find out the relation of W naught in terms of lambda 1 and lambda 2. So for case 1, that should be this is for kinetic energy is equal to K when wavelength is lambda 2 and kinetic energy is twice K, wavelength is 2. For case 1, for lambda 1, kinetic energy is equal to K. That's why I have found out this one. For case 2, again H nu is equal to K plus H nu naught Hc by lambda 2. For lambda 2, that kinetic energy becomes twice K Hc by lambda naught, because threshold wavelength for the metal will remain the same, it is same. So Hc by lambda 2 minus Hc by lambda naught is equal to twice K. Now this is 2. What we do here, using 1 in 2, just we replace the value of K by this value and we will put this value here. We will get Hc by, one more line we can write Hc is equal to 1 by lambda 2, 1 by lambda naught is equal to twice K. Now using 1 in 2, we will get Hc 1 by lambda 2, 1 by lambda naught is equal to twice. So in place of K, we will put this value Hc 1 by lambda 1 minus 1 by lambda naught. Am I right? So this will cancel out. So what we will do, lambda 1 and lambda 2 should be in one place, and lambda naught should be in another place because we need to find out lambda naught. So we have got the value of lambda naught as lambda naught is equal to lambda 1 lambda 2 twice lambda 2 minus lambda 1. Threshold wavelength is this one relation, and other one w naught work function is equal to hc by lambda naught. You are asked also to find out this value, so hc will remain same, and when we will put the value of lambda naught here, it will reverse. So we'll get twice lambda naught minus lambda 1 divided by lambda 1 lambda 2. These are the two values you are asked to find out. Very simple calculation, you can do very easily. Once you will do, you cannot forget. Now again the question is very simple. You first understand and we can do it within a second. You see the threshold frequency, of a metal is f, and when light of twice f frequency is incident upon it, the velocity of the electron, ejected electron or photoelectrons becomes v1, and when the frequency of the incident radiation changes to twice f, the maximum velocity of electrons changes to 5f. Threshold frequency of a metal is f, and when the light of twice of frequency is incident upon it, the velocity of ejected electron or photoelectrons with maximum velocity becomes b1, and when the frequency of the incident radiation becomes 5f, the maximum velocity of the photoelectron becomes b2, and find the ratio of b1 and b2. We know that energy h nu is equal to energy for the case 1, for 7, if the frequency is changes to twice f, means here the incident radiation h f changes from f to f, and it's become velocity, for velocity v1, that becomes energy, that becomes mv square. So what we get here is twice hf twice f by m is equal to b1 square. Now again h nu is equal to e for case 2, here the change of frequency is equal to this much, and the velocity become v2. Am I right? What here you get, this is 4f, and that is 8f is equal to 8 hf divided by m is equal to v square, v2 square. Very important and very simple things, h nu is equal to 1, then frequency changes from Now incident frequency changes when it is twice f from f. This is the frequency of the metal and this is the frequency of the light. So what is the change of frequency? That is, falling light is twice f and frequency of metal is f. This is first case. This is change. Now for the second case, the frequency of incident radiation is 5f and the frequency of threshold frequency is this. So these are the twice change of two change of frequencies. So for this you are getting this relation, and for case 2 we are getting this relation, and for this case the velocity is b1 and for second case velocity is b2, it is given, and when we will calculate we will get b1 by b2 is equal to half. Again very simple. So now we are shifting to de Broglie wave equation, where the again I need not explain it. A lambda equal to h by mb, lambda is equal to h by p, where h by twice me, h by twice me, v not h by twice mq. B here there is if it is electron, and if it is not electron, if it is proton and deuterium or alpha particle, then you use this one because there is q charge and there is change of charge here. Here if it is electron you use this one, if it is energy related to energy you use this one. You are always confused with these two. If it is not electron, it is proton, deuterium or alpha particle, then you use charge q, and if it is concerned with the energy, then h by root over me n equal to h by p is equal to momentum, mb p is equal to m by lambda is equal to h by mb. So very first one I will take a very simple one. See, again, the question is very simple and very often asked in entrance exam. A photon and the alpha particles have kinetic energy, have kinetic energy equal or same kinetic energy equal, and find the ratio of the wavelength. So what we know here is lambda is equal to h by p. Already I have written here. When a photon and alpha particle have same kinetic energy, find the ratio of the wavelength. We know this formula, but since there is energy, we'll use the formula h by root over twice me. So lambda is equal to, no need to write, simply you write lambda is equal to h by root over twice me. Am I right? So for photon we'll assume it p, and if the mass of photon mass of photon is equal to m, so mass of alpha particle equal to 4m, because alpha particle is equal to helium, its mass is 4. Each and every one is know, if it is 1 then it is 4m, so if it is m, it is 4m. So for photon you assume what you assume here, find the ratio of the wavelength. Energy is same, am I right? So energy is same and 2 is the constant, twice E is equal to constant, that is lambda p is nothing. You did not assume 2 and E, these both are constant. E is constant, so 2 is also constant, twice E is also constant, so h by m, or that is h is also for both the cases constant, so you assume 1 by m. So you write lambda p is equal to 1 by m, and lambda alpha is again proportional to 1 by, what is that m? That is m is equal to 1 by 4m. Am I right? So lambda p by lambda alpha is equal to root over 4m by m, is equal to 2 by 1. Very simple, nothing to explain much. You need not make it clumsy by assuming twice an electron. It is same for both the cases, so E and 2 are also constant. Need not to assume. H is also both the case constant. It will cancel out. Sometimes you are asked to show the graphs are lambda is equal to h by p. If it is lambda, it is FC sin if it ordinate, so ordinate will be P is equal to mb, momentum and lambda. The graph will be like this, very simple. You just keep it in your mind. Again, very simple. For case 1, you are asked variation of the wavelength. What will be? Lambda is equal to h by mb. What will be the variation of the if the velocity of the electron decreases? So from here you get what? Lambda is equal to inversely proportional to the velocity. If the velocity decreases, lambda will increase. For first case, lambda increase. Now for the second case, if the accelerated potential is increased, what's happened? We know lambda is equal to again a very simple relation I have told you, that if it is potentially given, you write lambda is equal to 12.7 √2 bar v naught into n naught. It is in Armstrong. So nothing but from this formula you will get it is extra I have shown you. You will get lambda is proportional to 1 by √2 bar b. Am I right? So if potential is decreased, lambda will increase. So if accelerated potential is increased, lambda will decrease. So in this case, lambda will decrease. Nothing to explain. You write the formula, and from the formula I find the relation, and from the relation you check out which one will be your correct option. Very simple. Once again you try to understand the formula, understand the question. Heavy particle at rest splits suddenly into two parts or two pieces with mass m1 and m2, and with non-zero velocities, and after splitting it moves with certain velocities. Find the ratio of the wavelength of the two particles. Very simple. The mass of the heavy particle equal to m, and mass of the particle before splitting the velocity is equal to v mv. According to law of mass of conservation of energy, we know that is equal to m1 b1 plus m2 b2. It is for first particle m1 moves with some velocity, and second particle m2 move with the velocity v2 by v2. So mv is equal to m1 plus m2 b plus b2. At rest, first happen. At rest, what's happen? That velocity is equal to 0. Therefore, mb is equal to 0. Then we are getting that equal to 0. At rest, we are equal to b1 plus m2 b2. So what we get here is equal to m1 by m2 is equal to m2 b2. Taking mod on both sides, m1 v1 is equal to mod m2 b2, or what we write here is equal to p1. This is momentum. P1 is equal to p2. That is say p1 is equal to p2. P1 is equal to p2, or you can write what is p. Lambda is equal to h by p. Therefore, p is equal to h by lambda. So p1 is equal to h by lambda 1, h by lambda 2. Therefore, lambda 1 by lambda 2 is equal to 1. Very simple. Nothing to explain. You see, we are explaining something in a very critical, in a very simple manner and simple way. You try to understand, you can very easily understand. This is equal to h by mb. So according to question, a proton and a deuterium have the same velocity. Find the ratio of the lambda p, lambda proton, and lambda deuterium. Lambda is equal to h by mb, where velocity is the same, h is also same, so h and b are constant, so lambda is proportional to 1 by m. So for the case 1, what happened here? Lambda of proton is equal to 1 by m. Mass of proton is equal to m, and mass of deuterium double 1h2. Am I right? Is mass is twice m. So what do you get here? 1 by m. So for case 2, what you get here, lambda alpha is equal to 1 by twice m. Am I right? So lambda phi by lambda alpha equal to twice m by m is equal to 2 by 1 is equal to 2 by 1. Again, very simple, nothing to explain. Now you need to choose out which of the formula here we will going to explain. Here we are going to use a proton and an alpha particle. It is not electron. A proton alpha particle twice m qv. We will explain. We will use the formula 1 by root over twice m q v, and since it is accelerated through some potential is v. Am I right? So what is the question? The question is a proton and that of alpha particle accelerated through same potential, v is the same. So for proton, mass of proton, say it is mass of proton, say it is m, and mass of alpha particle, you know it once again, all every earlier I have shown you, it is twice m. Now what is charge of proton? Charge of proton, say it is q. Then what will be the charge of alpha particle? It is twice helium. Am I right? So it is twice of q. So just you put the value here. For the case 1, alpha of proton is equal to 1 by twice mass is what? M. For proton m, charge is q, and b is the same. No need to change, or you need not write to the value of q. Then lambda, sorry, this is lambda. Therefore for case 2, that is lambda alpha is equal to 1 by root over twice, here m is equal to twice m, and sorry, alpha particle, it will be 4m. Am I right? So this will be 4m, and q is equal to twice q v. So what you get here is 1 by root over 16 m q v. So we are getting alpha p divided by alpha, sorry, lambda p divided by the lambda alpha. This will be above. Am I right? This will be 16, and this will be 2. It is root over 8. It is 2 root 4. So the answer will be like this. So this is all about, in short, about the first chapter. In the next class, I am coming with the nucleus of atoms of the second chapter with elaborate explanation, with lots of question, entrance exam question, solution of entrance exam question. Hope you have enjoyed the class with most enthusiasm, and please don't forget to subscribe, because each and every class will have more and more explanation on entrance as well as state and CBSE or NCERT course. Thanks for watching the video.